Good morning, everyone. Welcome to our virtual lecture. If you are not here last lecture, we started chapter 6. We started chapter 6 on atomic structure and electron configuration. What we started off with is looking at the properties of light, okay? Properties of light, and there are three so far. In section 6.1, we look at the properties of light. It behave as a wave, and we described or look at the three properties of a wave, which you know: wavelength, the amplitude, the frequency. You should be able to define those or state in your own words. What does the amplitude means with respect to the wave, the frequency, the wavelength. We looked at electromagnetic spectrum in relation to the visible region. When we say visible region in the electromagnetic spectrum, what are the domains of the wavelength? From 400 nanometers to 750 falls under what we call the visible region. We can see with our own naked eye. All electromagnetic radiation, right, or waves, you may call it, have the same speed or travel at the same speed. We call speed of light, and it has a constant which will be given in an exam: 3.00 times 10 to positive 8 meters per second. And we look at the relationship between that constant, the frequency, and the wavelength. Given a question relating to that equation, you should be able to do that. I pointed out to you that you should be able to convert the frequency from different units. We talked about the megahertz, gigahertz. How do we relate to the speed of light? Here is, all right, here is a few units you may be given in frequency. Nu, this symbol here on my whiteboard stands for frequency, and it is in hertz or H. Look at the PowerPoint slide where my cursor key is. This is hertz, or it is the same thing as per second, or you may see this in a question. It stands for units for frequency. So if you are given in kilohertz, megahertz, or gigahertz, you should be able to convert to hertz before you plug in that equation. I solved this problem on the PowerPoint slide, and here is the here was the solution for that problem. You see there, this is the problem we stopped at on this slide, calculating the frequency. This was the frequency. I don't think we went as far as this. Let me just go back to, this was the frequency of light, all right, given the frequency per second. Let's see that. I think we looked at that. Calculate the frequency. Yes, this is the question. Calculate the frequency of green light emitted by a hydrogen atom with a wavelength of 486.1 nanometers. All right. We know the unit here is in nanometers. We can just change that to, we change this to meters because of the constant is in meters. This is why we change that. Always the speed of light 8, this is not 8 meters per second. This is the reason why you always have to change to meters before you plug in this equation. C equals to the wavelength times the frequency times the frequency. You rearrange that to get the equation you need to solve that. So remember to pay attention to the units of wavelength before you plug in this equation. I'm just gonna give you this equation, and your job is to calculate what you are looking for. These are just few, different types of radiation with the common units used. I won't ask you to, give me the units used for each one of them, but for your own general knowledge based on the wavelength for visible as well as the outside the visible region. Today I want to start off from section 6.2, which is electromagnetic properties, which deals with the, so far we have looked at the properties of light, all right? But it does not explain the electronic properties of atoms. The property of light, which behaves as a wave, does not explain the electronic properties. There was some observation early scientists had noticed, and these are plug body radiation, photoelectric, and emission spectra. What does this mean? Remember the law of mass conservation that scientists had actually observed. Let's go back to the law of mass conservation. They could not explain why the mass of reagents always end up being equal to the mass of the product in a chemical reaction. And much later, they discovered that it has to do with the atom, that an atom cannot be what? Created or destroyed in a chemical reaction. Likewise, in section 6.2, there are some phenomena they couldn't explain. One of them is plug body radiation. What does plug body radiation means? Plug body radiation, from the word plug body, that means substances can emit. Plug body emits radiation of characteristic wavelength as a result of when they observe light energy. For example, if you hold on a nail or a piece of metal and you subject to or raise the temperature to maybe 1,000 and then remove from the flame or wherever, you'll see that it starts glowing. It was black before, but it starts shining later on. This is because of the radiation being emitted by that object. So if this is my nail, I hit it all the way to red hot, remove it, and then look at it, you will see that it is red. Why? Initially it was black, and then after hitting it to red hot, it started now glowing. We call that plug body radiation. It was black before, but after it started emitting radiation. They could not explain why. Like when you hit a nail, look at it, it will start glowing. We call that plug body radiation. Now there's this phenomena that when they shone light on the metal surface, electrons were emitted. We call this photoelectric effect. We could not explain why when light is, or when a metal surface, you beam light on the metal surface, electrons are emitted. We call that property, or we call that photoelectric effect. They could not explain as well. I mean, the light wave properties of light could not explain that. And then the last observation they made was the emission spectra. Emission spectra from the word emission, to emit. We will see later on that when light is, or when different gases are trapped in a container, an electric field is subjected to them, they start emitting light. For example, fluorescence tube. For example, the light bulb, right? The light bulb, it has some gases in there. Why? does it, or what really causes, is because of the emission spectra of the gases trapped in the bulb. All right. This is what I was talking about, the black body radiation. Initially, if you see this nail here is black. If it is heated to high temperature, it will start emitting radiation of characteristics. It will start glowing. We call these black body radiation. They will emit light, all right, or radiation of given wavelength. There is somebody by the name Planck who explained why, all right, why black body radiation. What is the reason behind that? It's because of the property of light, that light are emitted in particles. So if I can hold on to, if this is light beam stream, Planck is proposing now that light does not travel in form of a wave. Remember what we say, that light is behaved like a wave? We saw in chapter 6. Or section 6.1, that light behave like a wave. So we can remodify this to say that it is like this. Yes, it is like a wave, but we have the dots you see here stand for particle. We call it quantum for one and quanta for minute. So these are quantas of light or packets. We call it photon. So here, a particle, photon here is simply a particle. This is particle of what? Of light. If you can count like 1, 2, 3, 4, 5, we can quantify that a particle of light is called quanta. Quantum for one and quanta for many. All right, this is what is proposing, that behind the photoelectric effect and the black body radiation. Remember what I explained as far as photoelectric effect for Planck. He explained the black body radiation. Albert Einstein used the quantum property of light to explain the photoelectric effect, and photoelectric effect is the phenomenon by which metal surfaces emit or release electron when light with sufficient energy are shown on the surface. So he used the quanta to explain the photoelectric effect, that when light is shown on a metal surface, all right, electrons are emitted or released from the metal surface. And each metal, when we say each metal, depending on which metal in question on the periodic table, if light of sufficient energy, electrons are ejected from the surface, we call that photoelectric effect. However, at a lower energy, if we don't have enough energy, no electrons are emitted. No electrons are emitted. Why is it that the energy, all right, why is it that electrons are emitted or ejected from the surface? So in other words, if this is the surface, I want you to picture that. So there is a light coming here with like a wave. This is the surface. An electron will be ejected. You see that electron is leaving the surface, one electron. So if one photon, remember a particle of light is called photon. The equation you see here, I'll remodify this because this is what you will be tested. This is where you will come across in exam, that that equation I will remodify, that E and then subscript photon. That means energy of one photon. Not so many photons, but if one photon is just zooming, if this is just one photon. This photon is hitting the surface of a metal. Let's call this metal right here. It will hit a surface and one electron will be ejected. How do we calculate the energy of this photon? Using this equation, Albert Einstein used the Planck's theory and derive an equation used to calculate the energy of one photon, So this is energy of one photon, one quantum of light. Recall from section 6.1, this stands for frequency. We cannot talk about velocity down the line, and when I give you in the exam questions, what does this mean? This is the frequency. So here, this stands for, let me go to the next slide here. We call these Planck's constant. You don't need to remember or memorize this. This is a constant you'll be given, 626 times 10 raised to negative 34, and the units joules times second. This is just the constant, joules times the second. And if we are calculating energy, all right, if we are calculating energy, remember energy, SI unit for energy is joules. So frequency, this is frequency, and it is hertz, which is the same as per second. So that if you are multiplying joules times second times now the units for frequency per second, unit constellation, second and second will go and you'll remain with joules, just to give you how you reconcile with the energy of a photon. So I've just defined what this stands for. This is Planck's constant, and this is the frequency of that photon, and we can calculate the energy of a photon of light hitting the metal surface. So you'll be given that Planck's constant, and this is the constant. I don't want you to just pull your hair trying to memorize that. I'll give you that. All you have to remember is how to key in your calculator. You should be familiar with your scientific calculator and use the right key to key in the exponent, Now let's see how the question can be framed in calculating the energy of a photon of light. Calculate the energy of orange light emitted per photon of neon sign with a frequency of 4.89 times 10 raised to positive 14. So the frequency here, or at the outset, you need to remember that energy of one photon, subscript here, photon is given by this equation. This is not phi, but nu stands for the frequency. I know that the units for the Planck constant rather is times 10 to negative 34 joules times a second. This is joules times a second. And this 14, no, not 14, but 4 point, this is 4 point, it is the same as per second. It is the same as per second. So this is 6.6 times 10 raised to, this is 626. It's gonna be 6 times 10 raised to negative 34 joules times a second times the frequency, which is 4.89 times 10 raised to 14. This is the same as per second. If you are given in a different unit here, if it is megahertz, if it is gigahertz, if it is kilohertz, you got to change to hertz. You got to change to hertz. All right. Thank you. Thank you, Santi. I just let them in. Sorry, guys. I was busy on my whiteboard here. I'm using my iPad to work here. So thank you. So here is a question on how to calculate the energy of one photon. Let's see, before I just point out something here. You have to know how to use your calculator. This is 6.8. What I'll do is 6.6 to 6. All right. Exponential negative 34. If I were you, I'll also try so that you ask question if it doesn't work in your calculator. All right. Times 4.8989. This is exponential 14. Exponential 14. And I see this is 3.2. All right, 3.24 times 10 raised to what? Negative 19 joules, 19 joules. Some question might just, test you, how to convert to kilojoules or other units. Jennifer, since we are using exponent, can we use our own calculator on the quiz? Yeah, if you feel like it's that is gonna be easier, somebody raise or somebody put to my attention that the Honolulu calculator kind of like cumbersome. Yes, you can use that in your exam. So next time, I'll point out to that, Jennifer, so that I want you to take the exam with the calculator you know how to use. All right, different models have different function. Trust me, one time a student, every time if this was face-to-face, I go around the class, somebody say, I don't know how to use my calculator. Then I go around and say, this is how you key in, like when I want to write times 10 raised to negative 19 on my scientific calculator, second function, and then EE and whatever. So please familiarize yourself with the calculator. One student tried, I couldn't figure it out. I couldn't crack his calculator. And then another student in the exam asked me, how do I use my calculator? I said, I'm not gonna teach you in the exam, this is just exam. But if it was lecture, and then I'll show you when time comes in the exam, then you are familiar with your calculator. All right, so I'll let you know, I'll let you use that, Jennifer, thank you. I'll point out in the next quiz. And you notice that I changed the from Honolulu to lockdown browser. All right, we're gonna be working with lockdown browser. Nicholson, yes, we're gonna be working with lockdown browser. So coming back to this problem, please, when you see this equation, it is for one photon. I have seen questions saying that calculate the energy. For example here, calculate the energy of the orange light emitted by 1 mole. If I change to 1 mole of photon, that means you're gonna multiply this with a Avogadro number. You know Avogadro number, right? Just in case, if I say 1 mole, all right, equals to 6.02 times 10 raised to what? 23. 1 mole of photon. 1 mole of photon. That's what I meant to say. 1 mole of 1 mole. Right here equals to photons. So we will multiply that by Avogadro number. This value here. So this is for 1 photon. Okay. Well, I want to just break down further this equation right here, that some values may be given and you are expected to know. Remember, this is also true. Planck's constant times, all right, speed of light over what? Over the wavelength. That is also true because frequency is the speed of light over what? Over wavelength. In this case, you know, you may be given the wavelength and you are expected to know what this stands for. This is the speed of light, all right? Anthony, is that an H? Yes, this is an H. Thank you. Maybe my H is, this is an H. It's look weird, right? Let me just erase a little bit to really look like an H. Yes. Good H. Yes. Thank you. So here is what I was just trying. I don't want you to think that all question will look like this or you use that equation. At some point, you may be required to use this equation as well, because in section 6.2, we learned that frequency is the speed of light, which is 3.00 times 10 raised to what, 8 meters per second. And you may be given the wavelength and say, I know you only calculate in the lecture where the frequency is given. How am I going to calculate the energy, yet I'm not given the frequency? I have been given the wavelength. You got to use this relationship between speed of light and the wavelength to calculate the frequency, and then you plug it in that equation as well. I've seen questions along those lines. All right? So that is how to calculate the energy of a photon. Remember, Planck is talking about the photoelectric effect. When we shine light, all right, that is the energy of one photon, Okay. If sufficient energy, it will interact with what? It will interact with an electron, and an electron will be ejected from the surface. Now, there is the third observation early scientists noticed was the emission spectra. From the word emission to emit, this is a discharge tube. Most common discharge tube contain gases, different gases, and when they are subjected to, electric voltage, they emit light of characteristic color. You've seen neon, all right. You have seen argon headlights, shine, or hydrogen headlights. They emit that. This has to do with, all right. This has to do with electrons in an atom getting excited from the lower energy level to a higher energy level. We're gonna come back to that. Understand this emission is to emit. When atoms or molecules absorb the photons we're talking about in the previous section, they get excited. And when they come back, they emit light of characteristic wavelength. They could not explain earlier on or previously before this line spectra. This is what they noticed, that for a line spectra, this is what we're talking about. Line spectra right here is when light or light energy is absorbed by electrons of different gases. All right, they get excited, and when they drop down again, they emit light of characteristic wavelength. This observation here they could see, but they could not explain. But first, let's see this continuous versus line, because this is our focus line. Continuous means, you see like red is going this way, and then you might to yellow, and then you might to green, and then you might to, that is the continuous, like in a rainbow. But line spectra, you see from the word line, you see line of, different colors along the visible region of electromagnetic spectrum. You see 400 to 700, remember that region where we can see with our naked eye, we can see this is red, this is blue, and remember my region of yolk, crow, bananas in what? In vein to red is on this side, this is red. This is, cream, and then maybe violet on that side. For V on my whiteboard right here, this is just the colors I'm arranging according to where they fall in here. So elements on the periodic table, all right, this is for hydrogen. This is for neon. There is the, fingerprints, fingerprints, there's the fingerprints of all the elements on the periodic table. If you Google out online, you will see spectrum for different light. If you compare these two here, we have so many lines for what? So many lines for neon. And as even if when the number of electrons get more and more and more, we see a lot of lines. What causes these lines? I'm just gonna explain that in a moment. So from this slide right here, I want you to differentiate what we mean by line spectra and continuous. This is just white light. It was continuous, but different wavelength for different lights, all right? For hydrogen, remember hydrogen has only one what? Has only one electron. That's what we know. It's atomic number 1. It has one electron. And when we, all right, when the light is, or electric, when the electric voltage is subjected to hydrogen, this, and have some slit similar to what we have right here, a slit from the hydrogen light, you see these lines right here. This is what is seen for hydrogen spectrum. We have what, around 650 nanometers for red, around maybe 480. I haven't really calculated the scale right here, but around 386 here for violet. But nevertheless, you see 1, 2, 3, 4. 4 lines at a specific wavelength for hydrogen. And remember, there's only one. They observed this, but they could not explain why. What is happening? All right, we'll explain that later, or we'll see later on. John Palmer, all right, in 1885, he calculated those lines for hydrogen. In other words, these lines right here, they could see that the lines do happen at specific wavelength, and he was able to calculate or come up with an equation to calculate the wavelength. For what? For red, for, maybe this is green, this is violet. We call this Rydberg equation. Having worked with that, his formula didn't land. Remember, these are two different scientists. It's not the same person, by the way. He modified his equation to come up with what we call Rydberg equation, and this is the reciprocal of wavelength. All right. So if from this equation, wavelength, all right, wavelength is 1 over, this is called Rydberg constant, 1 over n, 1, this is square, minus 1 over n2 square, like that. Remember, this equation is to calculate this wavelength right here. How do we calculate to end up with 150? Before we look at example here, let me explain why or what is happening. From what we learned earlier on from the photoelectric effect, when an atom, all right, when an electron in an atom, if this is an electron right here, say photon, if a photon is just this, assume this is one photon, interact with that one electron, the electron jump from, this is n equals to 1, all right, to n equals to 2. We're gonna talk about the n. You know what n stands for from your intro to chemistry? I know some of you can relate to this. Remember, we're gonna talk about this model of an atom. This is the what? Nucleus. And these are called energy level. N equals to 1, n equals to 2, n equals to 3 as you go away from the nucleus. I will come back in detail to this, but in relation to what you see here from Rayleigh-Spark equation, when an electron drops from the higher energy level to a lower energy level, so this electron will be promoted to, say, higher energy level. We call this, we say that this is excited electron. All right. This is, right here, we say that this is electron at ground state. We call this ground state. Ground as in ground zero. Ground what? Ground state. There are two terms you need to differentiate this. When electron is resting to where it was before the interaction with the photon, here is the photon. When a photon, interact with an electron at ground state, it gets excited or promoted to a higher energy level. When it drops back to where it was, like that, is coming back to where it was, a photon is emitted. A photon is emitted, and that photon will correspond to the wavelength of each of the lights you see here. If it is a red light, you will see it as red light. It depends on where it is dropping from. So from this equation, this is where the electron is dropping from. Let me just write this, dropping from which energy level. And then here is dropping to, where the electron is dropping to in terms of energy level. That if an electron is promoted to n equals to 5, it is when it drops back again, this is our n or higher energy level. This is lower energy level where it is dropping back to. So you'll see that an electron is dropping from here to here. This is your lower energy level. This is the energy level. With this equation, you know what n stand for, you know what n1 stand for, n2 stand for. This is called the constant. You'll be given also, we call Rayleigh-Spark constant, and it is 1.0977 times 10 raised to positive 7 per meter. Do I expect you to memorize that? No, I don't expect you to remember that, but you will plug in the equation. Whatever you will do on this side, don't assume that that will be your final answer. You have to do the reciprocal of your value. Say, for example, let me show you. Say still on my left side of the equation, it is still 1 over the wavelength. And this one right here equals to 2, for example. I've done everything on the right side of this equation. I've done everything on the right, and I end up with 2. That means the wavelength will be 1 over 2, the reciprocal of that, or the inverse. So you have to find the inverse of your final answer on the left side, Where we are going to with this is to find the wavelength of a photon of light. And remember, these are small wavelength that the units are in nanometers, but because of this radius per constant, the units are in, or the unit for this R value here is in meters, you will change to nanometers. And remember, 1 nanometer equals to 1 times 10 raised to negative 9 meters, or 1 meter equals to 1 times 10 raised to positive 9 nanometers, whichever way you want to pick to change to nanometers and vice versa. That's what I want you to remember from the radius part. You may not see this term or name in the problem, but if you see that an electron is dropping or transitioning from point A to point B, know that this is where it is dropping from, and this is where it is dropping to. From my whiteboard here, N1 is where it is heading to. This is where it is coming from. You will see N1 equals to this, N2 equals to this, and so forth. And our N1, N2, this is the energy level. We're gonna talk about energy level later on, but I just want to jump the gun and explain what this N stand for. Now, Bohr, working with hydrogen, he explained now why we see this. Remember, they could see, but no one actually knew what was causing. Neil Bohr, or we simply say Bohr model of an hydrogen atom, he explained using what I just gave you here, that, oh, you know why we see red, we see this, it's because electrons are dropping from higher energy level to lower energy level. He was using hydrogen model to explain the lines. And his explanation is that electrons are transitioning from higher energy level to lower energy level, and they emit photon of characteristic wavelength. If it is 650, you'll see it as red. If it is around 480, then you'll see it as green. Or if it is around 386, you know, you will see it says this. So he explained this spectrum. Radius-Park came up with an equation on how to calculate the wavelength. You will see mostly this as hydrogen, because, you know, for multi-electron, it's not gonna work. So how do we use the Radius-Park equation to calculate the wavelength of an electron moving from n equals to 6 to n equals to 1? So at the outset, this is Bohr's model of an atom that, you know, we have the nucleus. This is the nucleus right here. And then this is energy level 1, n equals to 1, n equals to 2, and then n equals to what? N equals to 3, and so forth. This is the nucleus of hydrogen atom. So if it is dropping from that, we will plug in our equation. Remember, radius spark is 1.0 or 9,776 times 10 raised to what? Raised to 7 per meter times. It is dropping to 1 square, dropping from 6 square. Remember where it's saying dropping from? If you just joined in, this is where dropping from. This is 2. It is dropping from that to that. It is dropping from that to that. It is technical in the sense that, look at the units. They want you to express the answer in nanometers, but there is the component of meter here. If you fail, you will think that whatever the value you'll get is in nanometers. The value you'll get from this equation will be in meters, but the answer is required to be in nanometers. Let's solve first of all the equation. All right. If you plug in your equation, this is, if you want to, let's see, you can do what you have in your parentheses first. All right. 1 minus 36. I see this is 1.077. No, this is 9,776 times 10 raised to 7 per meter times, all right, 0.97, this is 722. All right, so we just multiply that times 1.09776 exponential 7, exponential 7. So here, this is 1 over equals to 1.0, 1, 2, 3, 4, 5, 6, 7 times 10 raised to negative 7 per meter, reciprocal of that. So if we find the reciprocal of that, all right, reciprocal of that, 1.067 exponential 7, this is 7. Reciprocal of that, I see this is what it is now. Lambda equals to 9.37 times 10 raised to negative 8 meters. Negative 8 meters. Please, let me back up again. Don't make a mistake. If you look at this equation right here, this is where it is dropping from. It's dropping to from n equals to 6 to n equals to 1. All right, so I know you can handle that. Remember, this is per meter. This is a constant. You'll be given that. No need to worry, but with this homework, you get to flip the page in the text. They're not gonna give you in the problem, but I'll give you in the exam. You have to remember that the unit is in per meter. So 1 over, I have to find the reciprocal of this to end up with the, the wavelength. And the unit is in meters, but the question is in nanometers. Somebody might assume if they don't reconcile the units, they'll think that, oh, maybe the instructor forget, and then you just pick this as 9.37 times 10 raised to negative 8 nanometers. That's wrong. You need to use the conversion factor. I want to get rid of what? I want to get rid of meter. I'm looking for nanometer. I'm looking for nanometer, and 1 nanometer equals to 1 times 10 raised to 9 nanometer. So that meter and meter will go away, and I end up with 93.7 what? 0.7 nanometers. That's how you calculate the wavelength of an electron transitioning from a given energy level to another energy level. Okay, what really makes chemistry like look hard is sight things as forgetting the units, and you'll be like, I read and I understand, you know. I was given an equation. What am I doing wrong? You know, what's wrong with my calculator? It's because there's some knowledge you learn elsewhere, you are expected to recall as you go down the line with the course. Believe me, when you get to Chem 2, all right, you know, they will expect you to recall some, not all of them, some of the concept you learn in Chem 1 to apply in Chem 2 to move on, all right? So likewise here, you are expected to know that how do I change from meters to nanometers? Nobody may not give you this conversion factor. You got to know how to change that. And then you move on to that. Any question? So that's what I wanted to point out, you know, how to calculate the wavelength of an electron. Remember those. Practice make perfect. Please work more on how to calculate the energy of an electron, transitioning from higher energy level to low energy level. Let's go back to Bohr's model. Here, I want even to label this as Bohr's hydrogen. You know, when we say Bohr's model, hydrogen model of an atom. Yes, he is only working on hydrogen, just trying to paint a model of hydrogen atom, not helium, not any element on the periodic table. Bohr worked only with what? With hydrogen to propose a model of an atom. And he explained this, that, you know, electrons are only found within, all right? Electrons are only found within specific energy levels which are permitted only in orbits of certain radius. You know, there's sometimes here, it might be the first time you're looking or you forget. What is an orbit? Let's just define this first. Orbit is space in an atom. Where there is what? There is high probability of, this is high, H, of finding an electron, finding an electron, finding an electron. An orbit, so when we say orbits, radius, no, this is orbital, sorry about that. This orbital, whereas orbital, this is stand for orbital, sorry about that, orbital, T-A-L right here, orbital. And orbit here is not, orbit is just circular path around an object. You know, the Earth goes around the sun following its orbit. It's not anywhere. The moon goes around the Earth following its orbit. It's not anywhere. All right. That's why we talk about the equator. So orbit is from number one there. This is an orbit. This is an orbit. This is an orbit. He is proposing that orbits of certain radius from the nucleus with specific energies permitted for the electron in hydrogen atom. Remember, there is only there is only one electron. So he's talking that electrons are in energy level 1, energy level 2. Remember what I said earlier on, n equals 1, s equals 2, n equals 3, and so forth. Ground state, that is the first energy level. Now, when an electron in n equals to 1, right there, an electron in n equals to 1, get bombarded by a photon of light, it will jump into a higher energy level. We call that excited, what he said, excited state, excited state. And it has higher energy. When it drops back, look, when it is dropping back to where it was, it emits light, photon. Look at my cursor, a photon is emitted, and we can calculate the energy of that photon. When it is going up, a photon is absorbed. So when it drops back again, this is dropping back to where it was, a photon is given off. Photon is given off. A photon is given off when it is dropping to where it was. And then can you go back to orbital real quick? Let me just explain, because there will be two terms here. It sounds the same, but they don't mean the same thing. Orbital is an orbital. We will describe using other numbers later on, but for now, an orbital is a space within an atom where there is high probability of finding an electron. All right, an orbital is a region of space within an atom where there is high probability of finding an electron. For example, we have this is energy level 1. We have orbital in energy level 1. We have energy in level 2. Otherwise, where there is no circle, that's just an empty space, and we cannot find an electron there. So there is a region of space within an energy level where we can find an electron. We call that orbital. Orbital right here within an. This is where the electron resides. All right. I can call this maybe your, maybe your apartment, for example. In the apartment complex, that there's a specific, room or your house or wherever where you live. It's not anywhere in the apartment complex. So likewise, in an atom where there is high region of finding an electron, we call it an orbital. We'll come back to this again. I hope, Anthony, that clarify or differentiate what I'm talking about here. Orbital, orbit and orbital, they are different. So now we will come back to orbital again, and I'm going to mention to you, I've just explained that. So when an electron drops down from higher energy level to lower energy level, a photon is given off, and we can calculate its energy. There is an equation for calculating energy. We will just come back to that in a moment. So we know that photons are given off when electrons drop. Let's for a minute, if an electron is if an electron is occupying this energy level, and in the nucleus, we have the protons, what is it preventing that it's not colliding into each other? Remember, positive and negative to collide, to attract. Positive, positive, they repel. Negative, negative, they repel. And positive, negative, they to attract. And at that time, classical physics, that's what I'm talking about, positive, negative, you know, attracting each other, they knew, and they could prove that positive and negative do attract. Question to put at that time was like, what is it really preventing this electron from crashing into the nucleus and just the atom collapse? He explained that electrons are only occupying allowed energy level. So this is allowed, this is another allowed, this is another allowed, this is another allowed. It cannot leave that, all right? It cannot leave that energy level. It is just within specific energy, and therefore they do not spiral. Why spiraling into the nucleus? Why are we saying into the nucleus? Because in the nucleus, we have the protons which are positive, all right? And it cannot also spiral away out of the atom because it has to be only allowed energy level, all right? And he stated that also the energy of an electron can be calculated using the this equation, which we looked at earlier on. Remember, energy of a photon of light. So when we talk about photon of light here, this is the equation, and we calculate earlier on. All right, we calculate earlier on. This should make sense now. What ground state means: electrons in the lowest energy level are said to be in ground state. So if electrons are right here, we say they are in ground state. If a photon of light interact with that electron and they jump into a higher energy level, we say excited state. So if it is starting from n is equals to 1, if n is equals to 1, and 1, 1, 2, 3, 4, if this is n equals to 4, we say that this is excited state. But if an electron in hydrogen is the fast energy level, we say that is in ground state, So this is what I explained earlier on. What is an orbit? It's just a circular path around the nucleus. And we can calculate the energy difference between two. We can calculate the energy between two orbits using the equation. This means change in energy. Change in, this is means change in what? Change in energy between two energy level 1, this is Y, energy level 2, energy level 3. For an electron dropping from, this is the final where the electron is dropping to. This is where it is starting initial. This constant is the same as, it's not, you know, radius back, but you will be given in order to find the, energy level. There are two things here. One is either electron or energy is absorbed or energy is released. Energy is absorbed or energy is released. If it is positive, what does positive means? Positive delta E means energy is what? Energy is absorbed, you know, endothermic. That means it's carrying in positive value. Remember, positive enthalpy of reaction. And negative here means what? Energy is released. Energy is released by an electron. So plugging in, there is a negative Simple right here. There's a negative sign here. 2.18 times 10 to negative 18 joules. What you see in parentheses here is now the energy levels where the electron is dropping from and where the electron is ending up with. We don't want to, either way, you see when we have final and initial, it could be from 1 to 2. If it is from 1 to 2, where is it ending to? So it's not like the one dropping where we saw earlier on. You have to pay attention in this equation for calculating the energy. The starting and the final. You know, an electron can be from 1 to 2. So you plug it here, 2 will be our, you see this? If the electron is transitioning from 1 to 2, that means our final is 2 and our initial is 1. If the electron is transitioning from 2 to 1, our final is 1 and our initial is 2. If our electron is dropping from n equals to 3, that means from 3 to 1, then we will have to plug the respective. The question will be specific when calculating the energy. And of course, the energy will be either positive or negative, either positive or negative. If it is negative, that means photon is emitted. Anything less than 0 is negative. That means photon is emitted. It is dropping down. If it is positive, photon is absorbed. That means electron is going up. It was absorbed, positive, negative. And with that, let's see how we're going to use that equation. All right. The energy in joules required for an electron transitioning in both hydrogen. Remember, we're still in hydrogen. From n equals to what? 1 to n equals to 3. So we're just gonna plug in this equation, all right? Starting from final, this is our initial. So our initial is 3, all right? Our initial is 1, our final is what? Is 3. With that, we know change in energy is given by negative 2.18 times 10 raised to negative 18 joules into final. This is 1/3. This is our final. I squared 3 minus 1/what? 1. 1 square is 1. Trust me, if you flip the numbers, it will not play out well, and you may see in the multiple choice. So here in parentheses, 1 divided by 9, that times 2.18 exponential negative 18, and I see positive. This is positive. 1.94 times 10 raised to negative 18 joules. Joules. That is D is in David. D is in David. This is a constant. You'll be given that. And here, remember, this is always final. And this is always the initial, final initial plug-in, and you end up with the units. And this is for hydrogen atom. This is for hydrogen atom. Calculating the energy of an electron transition from one energy level to a different energy level. Now, there is a reason why I told you porous hydrogen atom. It could not explain multi-electron system. Multi-electron system is either hydrogen and anything you can think beyond hydrogen. Any element on the periodic table with two or more electrons. It only works for hydrogen with only one, with only one electron. So how are we going to explain the multi-electron? All right. Well, this theory actually work for, or still explain where we are with the quantum mechanical model of an atom. That his theory explained that atoms move around. Let's just, from here, what we know, he proposed that electrons, or in an hydrogen, electron move around the nucleus in a wave like, so it is like a wave. Electron move around the nucleus like a wave, but he could not explain multi-electron. These are the things which really still hold, that electron exists in certain discrete energy level. We're gonna talk about the quantum numbers later on. Whatever he proposed is still valid up to today in the model of an atom, that yes, electrons occupy energy levels, energy level 1, energy level 2, energy level 3. It is also true that electron transition from one energy level to another energy level, still valid, but he could not explain or come up with multi-electron. So what are we? What are the take-home points from section 6.3? One, we know electrons occupy energy level 1, energy level 2, energy level 3. An electron move around the nucleus like a wave, all right, like a wave. So remember, wave property of light. Now, section 6.4, all right, section 6.4, somebody by the name de Broglie, all right. It is a note that if you guys, those guys, you know, Planck's, Johannes, Redersberg, and you know, they could calculate the wavelength of a photon, right? You can calculate a photon that, okay, it is a note that if actually light behave as matter is just a wave, like a wave has a wavelength, then matter can also behave as what? As light. And if matter can behave as light, we can calculate its wavelength. We call that de Broglie wavelength. That is very specific. All right, de Broglie wavelength. De Broglie, he was a French scientist who came up with a theory that if light behave like matter, and then matter can behave like light, that means we can calculate the wavelength of anything. And this is called de Broglie wavelength. This is, and you will see in the question, calculated de Broglie wavelength. It's gonna be de Broglie wavelength. And it is given by, I think, Anthony or whoever asked whether this is H. Yes, this is H. Let me just write my H correctly. And M, this is not frequency, it is V. We call this D and then Broglie wavelength. And you'll see question that, you know, calculate the de Broglie wavelength of this, calculated de Broglie wavelength of that, calculated de Broglie of any matter, not light, any matter, you know. Matter can exhibit wavelength. And this is what I was thinking, like, Every time I'm driving down the interstate, have you ever seen those 18-wheeler, like they were wobbling like this? Wobbling like this, and you're like, let them go, let them go. They might just, because they're traveling like a wave. Even when you see somebody walking, sometimes you have seen somebody like, we can calculate your wavelength if you ever walk like this on the street. We can calculate your wavelength. Or if you are riding your, your skateboard, somebody be doing like this, somebody be doing like, we can calculate your wavelength if we want to, using what we call the Broglie wavelength. Let me break down this. This is called the Planck's constant. It's still the same value we looked at earlier on, 6.626 times 10 raised to negative 34. And this is joules times second. Now, this is mass in, always mass in kilogram. So you should change the mass to kilogram. In kg, always change the mass to kilogram. Always, this is, V is speed. This is a speed, or you will see this as velocity. This is velocity in meters per second, in meters per second. So if something is moving at a given speed, for example, miles per hour, you got to change to meters per second. If the mass is given in grams, you got to change to kilogram. If mass is given in milligram, you got to change to kilogram. If it is given in ounces, you got to change that to kilogram. Why are we changing those units? It's because of the Planck's constant, which we cannot change. And what we saw earlier on at the beginning, when we look at the energy and the kinetic energy, mass times square, velocity square. Remember this? We can relate this to the units. Nevertheless, I want you to remember that this M stands for mass in kilogram, and V is speed or velocity, and it should always be in meters per second. Once you plug in the Planck's constant, and that will give you the Broglie wavelength. And it's not for light, it's not for photon, it is for objects in the real world. You may see like a baseball, when the pitcher or whoever, I'm not into baseball, when they draw that, we can calculate the Broglie wavelength of a baseball. We can calculate the Broglie wavelength of a soccer ball, for example. We can calculate the de Broglie wavelength of the plane, and anything, any matter, something you can see, even the electron. With that, this is called the de Broglie. Here is a question, and you'll see in the problem that what is the de Broglie wavelength of? What is the de Broglie? Calculate the de Broglie. Every time you see de Broglie wavelength, I've underlined and bolded what you need to pay attention, that always mass has to be in kg. Always speed or velocity has to be in meters square. So the only thing we need to do in that is to, all right, and it's not reciprocal. Don't think that this is going to be the radius back where you have to do the reciprocal. No, you don't do with this. It is 6.626, all right, times 10 raised to negative 34 over mass will be in kilogram. So this is the mass in kilogram. I divided that per 1,000. All right, per 1,000. All right, per 1,000. This is kg. times the speed. This is 5 meters per second. This is joules per second. And then it turns out that 1 joule is kg times meter square over second square. So that second and second square will go, the second and second will go in that, and meter and meter will go with that. There is the meter square, it's gonna cancel out. 1 meter will go with 1 meter in meter square. And kg will go with the kg there, you'll remain, and the joule will go with the joule there, you'll remain with the wavelength in meters, So using the Planck's constant, 6.626 exponential negative 34, all right, divided by 0.025 times 5. And with 5 this is 5.3 times 10 raised to negative 33. This is meters. This is the de Broglie wavelength of an object moving. You can't even see. You know, that means, you know, let me just show you. The distance between here and here is this. This is a small, how many zeros? Like 30 zeros, you know, you can't even see, like, you may not even recognize that this thing is wobbling like this, that there is a wavelength. All right, let me just go back again and explain, Andrew. Let me explain the unit cancellation. Previously for kinetic energy, you remember kinetic energy? Let me just go back to, you know, I have m v square, right? Remember v square and the mass was in kilogram. So this one, it turns out that 1 joule equals to kilogram times meter square second square. This is how we relate now, you know, the energy of a moving object. This is the kinetic energy we talked about earlier on. I want you to relate or remember that relationship between joules, which is the unit of energy, with the units you will end up with when calculating the kinetic energy. This is what we learned earlier on. Now, going back to what we talked about in terms of de Broglie wavelength, this one right here, this is Planck's constant. And this is the mass in what? This is the mass in kg, and this is the velocity in meters per square. Let me reconcile the units. If the top part is in joules times second, remember that's the unit for Planck constant, over the mass in kg times, let me just multiply that, velocity or the speed in meters per second. We want to just convert that to wavelength using this conversion factor. There is another conversion factor here to convert to length, meters. 1 joule equals to kilogram times meter square second square. Where am I getting in this? From this one, which was something we went through earlier on, joule. You'll see this, or if you can recall, or if you don't recall, this is what it is for kinetic energy, something moving. We can calculate the kinetic energy of a moving object. This is something moving, all right? We can calculate its kinetic energy. And then we want to relate with energy. So that is why I'm using this last conversion factor, which, you know, you don't see it. So let me cancel out, and then you'll see how the meter will remain for the units for wavelength. The joule will go away, the joule will go away, and the joule will go away. The second here, 1 second will go with that, and then it's gonna go with that. And then this second right here will go with that second right here for the second time. The kilogram will go here, and then the kilogram will go there. And then the meter here will go, and then the meter will remain with only meter here. There is nothing remaining to cancel that meter. That is, you know, the cancellation I need to know. Do I know? I'm not gonna ask you, show me how you cancel that. If you know that I need to, or whatever I will end up with, I'll pay attention to, this has to be in kg, and this has to be in meters per second. This has to be in kg. The rest we should come out clearly. You know, if somebody say that, how did the joule in the Planck's constant disappear? You know, you may say that you're trying to follow the units, and that's how the units reconcile. I hope that take care. Thank you. I appreciate it. But in the exam, if you know that's behind the scene, that's what's going on. And this is a classic example. This is a classic example what I just mentioned, that they expect you to remember that, oh, I learned this not too long ago. Yeah. So the answer for this one is B, 5.3 times 10 to negative 33. Please try on your own that you get the same answer. If not, let me know, and I can. If you cannot get what I'm getting right here, or what we are getting, please get in touch with me, and I'll walk you through your calculator. And then somebody mentioned earlier on and requested, for the sake of the Honalo calculator, you know, you're gonna use your calculator so that you get to use what you have learned and you're familiar with. All right. So we can calculate the de Broglie wavelength of an electron. Let me just show you where we are. Before we talk about the uncertainty, Heisenberg uncertainty, this is where we are. That electron is moving around the nucleus following what? It's like a wave. It's like a wave. This is an electron going around the nucleus like a wave. That matter can behave like a wave. This is the nucleus right there. Electron is going around the nucleus like a wave, because we know matter can behave like a wave. It's not going just straight like the way Porte had actually postulated, no. Based on de Broglie proposal or principle or law, that yes, indeed, we can calculate the wavelength of any matter, any object. Then we can calculate the de Broglie wavelength of an electron going around the nucleus of an hydrogen atom. Yes, we can do that. And then this guy you see on the picture, his name is called Heisenberg, all right? Heisenberg came up with a principle which states that it is so hard to know two things precisely: the momentum and the location of or the position of an electron within the atom. That it is so hard to know, you know, where the electron at a given point. You know, the more you know the other one, the more you compromise the other one. We call this the Heisenberg uncertainty principle. Uncertain, we are not certain. Let me give you an example. I don't know if this will make sense. If there is like a sports car, which, you know, it can cruise to maybe 500 miles per hour, we can know the speed. But it is very difficult to know the position if it is cruising at that speed, you know. Maybe by the time you're like, oh, it is at Jacksonville, it's gone. Just like the jet fighters, before even you see, you just look in the sky, you don't see anything. All you hear is sound, it's gone. Because the speed is so high, you can't tell the position. But if there is like a huge truck, 18-wheeler cargo truck, moving at a snail pace, we can know the position precisely, but the speed is, you know, is compromised. It's not moving at the same time. So it's hard to know both the speed and the position of an electron around the nucleus. For example, if we can freeze this electron right here and say, oh, the electron is right here, then it is no longer moving. We have compromised the momentum here, speed. And this is the position. This is called the uncertainty principle, that we can calculate the uncertainty in the position. And this is Planck constant, it's the same value, 6.6 times, this is 26, times 10 raised to it. Negative 34 is the same thing we had before. This is where you see X here, this is an certainty in what? In position that we are not certain. And then that equation right there, this is uncertainty in velocity or speed. Uncertainty in velocity. That equation I can should be like this: delta x times mass times change in position, like that, greater or equals to 4 pi. You know what pi is? This is 3.14. This is 3.14. So this is uncertainty in velocity. And this is uncertainty in position. We cannot know both position and at the same time be precise in knowing the velocity. Yes, Santi, the correct answer was B. Thank you. I'm just looking at it right now. Santi, the correct answer. Yes, thank you, Drake, for pointing out that the correct answer is B for that previous question. So now the uncertainty principle has to do with the position of an electron. If this is the electron going around, there is no way we can know the position and the momentum. This delta V should be in between the two. The equation should look like this on my whiteboard, so that if we are looking for uncertainty in position is greater or equals to the Planck constant at the top of 4 pi times mass times change in or uncertainty in velocity. This is one equation you can be asked. This is H, this is H, this is equation 1. Or if you're looking for uncertainty in velocity, is greater or equals to Planck constant 4 pi, all right, 4 pi times mass times uncertainty in velocity. In position. This is position. This should be X, uncertainty in position. Mass should be in kg. And velocity meters per second. So this is equation 2. This is equation 2 by rearranging the first equation. The constant pi 3.14, you know that. Pi is 3.14 and 3.14, which you can plug in to get that. All right. Let me solve the first equation. You will solve the second one, and we will start from here next time. It is now 12:26. I'll solve the first one and try the second one, and we will pick up from there next time. From the uncertainty principle, using Eisenberg uncertainty principle, calculate the uncertainty in position. So this is the equation. You rearrange the equation to get this. This is what we are going to use, equation 1. Equation 1. Planck's constant is 3, but 6.6 times 10 raised to negative 34. 4 times 3.14. The first two numbers, these are constant given from this equation. 4 pi, I have right there, times mass times uncertainty in velocity. The mass is given in milligram. You got to change that to kg. All right, times this is 1.5 what? 0 milligram. I'll multiply by 1,000 what? 1,000 milligram equals to 1 gram times 1,000 what? 1,000 grams equals to 1 kg. 1 kg. I'm just changing the mass to kg. Changing the mass to kg. So 1.50. It is times 1.5 times 10 raised to negative 6. That is kg. I had to change the mass to kg. Mass should be in kg. Now here, it is not speed, but we are looking at the uncertainty. Uncertainty is plus or minus. We care less about this. This is moving at this speed. V is not, this V is not the velocity, it is the uncertainty. Even in this one, this is the uncertainty part, not the whole speed. So in my calculation right here, I will multiply by 0.01, the uncertainty. All right, it is not the speed of whatever you're looking for. So if we divide that, 6.626 exponential 34, all right, divided by 4, divided by 1.5 exponential divided by 0.01. I end up with my calculation is 3.5 2 times 10 raised to negative what? Negative 27. And you indicate this is not equals to, we don't say equals to, it is, we use this value here. It is this symbol right here, greater or equals to, calculate the uncertainty in position. In certainty in position. I want to stop here today. It is now 1:31. I'll stop sharing my screen. Thank you for joining in today. Please stay safe. Be careful out there. Sanitize. Stay home. Please minimize your outdoor activities to essential trip. That's what I'm doing too. I have my sanitizer in my car. Everywhere I go, I have my sanitizer. Have mask. All right. Thank you. See you next week. Class is ending now. Thank you.